In this video, we'll be discussing properties of different power series. This corresponds to section 6.2 out of the OpenStax Calculus book, volume 2. Let's review briefly what a power series is. Remember that a power series is basically a type of series with terms that involve a variable. The entire power series concept is based on the idea of a geometric series. More specifically, if we let the variable be x, then all the terms of this series involve powers of x. This means that power series, in a sense, have two different variables involved. There's the variable which is the limit of the summation, so the index of summation n, and then there's the variable that is part of the summand, which is x. We can center each power series at a finite real number, usually called the center. We usually use the lower script italicized letter A to represent the center. Here you will see a generic power series centered at the non-zero value of A, and here you will see a power series which is centered at the value of 0 since there is no A. You can see that in both cases it generates what amounts to essentially an infinite polynomial. The power series will converge provided that the center x or x minus a is less than 1 or greater than -1. In other words, it converges under the same conditions as a geometric series, since it is based on a geometric series. Now let's look at different ways of combining power series to build new power series and represent different functions. The goal of this video is to learn how to combine power series by adding them and subtracting them, and to learn what the interval of convergence will be when you add two power series that have different intervals of convergence. We'll also learn how to multiply power series by powers of the variable or by constants or by substitution. This will be a pretty simple process, and this one will not cause a great deal of difficulty in doing the homework. The third objective, which is learning to multiply two power series together, is actually a quite difficult area of study, and we will just do a minimal number of problems out of that learning objective. The last learning objective is to differentiate and integrate power series term by term. This is something that you will more commonly see on an exam. So at the end of this video and at the end of section 6.2, the primary learning objectives for you to master would be the first, second, and fourth. One of the things that's important about power series is that it will finally give us a method for representing new functions that cannot be written in terms of elementary functions. We've seen elementary functions before when we tried to integrate certain functions for which there was no known antiderivative. By an elementary function, we mean that the function can be represented by sums, differences, products, quotients, powers, roots, something related to the known functions we've already studied, namely polynomials, trig functions, inverse trig functions, natural logs, and exponentials. We could also include the hyperbolics in this group. When we cannot represent something in terms of one of those elementary functions, we say that it is not representable in terms of elementary functions. And there are some integrals that we've seen that have no known antiderivative in terms of those elementary functions. Power series, on the other hand, will allow us to write down a definition for these functions, and then we'll be able to solve problems that previously we haven't been able to address. On this particular page, you'll see that we are giving the rules for combining power series through addition and subtraction, represented by the plus or minus here in the formula. For simplicity, the book only gave the formula in terms of a power series centered at x equals 0. That is, where the value of lowercase a is equal to 0. However, these also hold for any power series that is centered at the value of x equal to a, where a is not 0. In other words, it will hold whenever, instead of your base being simply the variable x, you have instead the base being the variable, the quantity, x minus a. Let's take a brief look at what these mean. Let's suppose that you have two power series, c sub n x to the n and d sub n x to the n. Individually and separately, they converge to the functions f and g on some interval I. Now, in this theorem, it says that the interval is common. In fact, the interval does not have to be exactly common, but there does have to be some overlap of the intervals of convergence. For example, let's suppose that c sub n x to the n converges to the function f, but only provided that x is between -2 and 1. If the series d sub n x to the n converges to the function g, but only from 2 to 5, then there's no overlap between those two power series. One converges between -2 and 1, and the other between 2 and 5. This would imply that you cannot add the two together because they do not have any overlap or any common interval of convergence. Whenever you have slightly different ones where there is overlap, you will take only the minimal amount of the overlap to be the interval of convergence of the sum or the difference of the two power series. Whenever you find that power series have no overlap, it doesn't mean that you can't represent the function. It simply means you need to find a different power series with an interval of convergence that is closer to the one you're looking at. So, for example, what is the rule? The rule is very simple. If you add two power series or you subtract two power series, it will converge to the sum or difference of whatever they individually converge to on the interval of overlap. If you have a constant m greater than or equal to 0 and any real number given by lowercase b, then the power series of b times x to the m power times c sub n x to the n power will converge to b times x to the m power times f of x on I, given, of course, that c sub n x to the n up here converges to f of x in the original. In other words, if you want to multiply by a constant, simply multiply the constant by whatever the power series converges to. If you want to multiply by some power of x, simply multiply that power of x by whatever the function the power series converges to. This also means that you can take and substitute something in place of x. So instead of having x to the n, and instead of multiplying by another power of x, you can instead substitute a different power of x in place of x. And it will again converge to whatever the original power series converted to, but with that substitution in place of x. Let's consider example 1. In example 1, we want to use partial fractions to find the power series of each function. Then we will find the interval of convergence, I. Our function is 3 divided by the two binomial quantities x plus 2 times x minus 1. First, we need to use partial fractions to separate it into two separate fractions. You'll see here that what I've done is split up the original rational expression into the sum of two fractions, a divided by x plus 2 plus b divided by x minus 1. I was able to then solve for a and b and got b to be 1 and a to be -1. This let me rewrite the original expression in terms of the fractions 1 over x minus 1 minus 1 over x plus 2. I've recopied here the formula for a convergent power series in its geometric form by comparing the formula 1 over 1 minus x to the formula for a convergent geometric series, a first divided by 1 minus r. You'll notice the two fractions I have are not written in terms of 1 over 1 minus x. I need to have 1 in the numerator, which I have, but I'm not starting with a 1 in the denominator. I need to reverse the order of the terms in the denominator by factoring out a -1. Factoring out a -1 will lead to a double negative on the second one, circled in purple. This will let me rewrite it in the opposite order, 1 over 2 minus x minus 1 over 1 minus x. Now I can multiply the first one by the unit fraction 1/2 divided by 1/2, which is just equal to 1, in order to convert that 2 into the number 1. I must have both a 1 in the numerator and a 1 as the first part of the denominator in order to get it into this power series formula. If I have something other than a 1 on top, I can simply pull it to the front as a constant coefficient factor. This lets me rewrite this expression here, the difference of the two fractions, as 1/2 over 1 minus x divided by 2 minus, and then 1 over 1 minus x is, of course, the power series formula. So it gives me the sum from n equals 0 to infinity of x to the n. The next step, of course, is to rewrite the one in purple that you see here in terms of its power series formula. That would be pulling the 1/2 to the front as a constant coefficient factor, which leaves 1 over 1 minus x over 2. X over 2 will replace the variable x in the power series formula. This will let me have x over 2 in the power series formula with a constant coefficient factor of 1/2 on the outside. This lets me write what you see in the next line. The last line in red is the final resulting formula for the two power series, resulting from the partial fraction decomposition of the original rational expression. The next step, of course, is to try to get this into one power series form. In other words, to rewrite it as a single power series. To do that, I can simply drop the second power series notation and write it as minus x to the n. I also brought the 1/2 power, which was on the outside, to the inside for the first summand. Now, I can separate the x to the n from the 1/2 to the n from the first summand, writing the 1/2, which was the constant coefficient factor of 1/2, and then 1/2 to the n, which was this 1 over 2 to the n. This will give me x to the n as a constant, or not a constant, but rather as a common factor in both terms of the summand. Then I can factor the x to the nth power out of the summand and write it in this form here. The 1/2 times 1/2 to the n gives me a 1/2 to the n plus 1. Factoring x to the n off the two terms leads to 1/2 to the n plus 1 minus 1, all times x to the n. Now let's take a look at the next example. In the next example, we are to write each series as a rational function, then find the interval of convergence. Here is the original problem here on the left, the sum from n equal 1 to infinity of 1 over x to the 2n power. We need to rewrite this in its power series representation. I've recopied here the power series form in the power series form and also in its rational expression form to compare it to the convergent geometric series. The first thing I would do is take the x to the 2n and lift it to the numerator by changing the power to -2n. Then I would separate the -2 from the n by writing it as x to the -2 to the n. What would the next step be? Now that I have a base being raised to the nth power, I can use the formula here and replace the variable x in the rational expression form with x to the -2. You could also think of x to the -2 as 1 over x squared. This will let me write the next few lines down. This becomes x to the -2 over 1 minus x to the -2. Now, Why do I have this extra x to the negative 2 here that does not appear in the formula here? The reason is we have to compare what a first is. In the formula, n starts at 0, which is why a first is 1. In our problem, n does not start at 0, n starts at the number 1. If we were to plug 1 into our original, we would find that the first term in our series is x to the negative 2, or 1 over x squared. So when we convert to our formula, we have to use the true value of a first, which is x to the negative 2, when we write it in the geometric series form. This gives us x to the negative 2 over 1 minus the thing being raised to the nth power, which is x to the negative 2. The next step, of course, is to rewrite this in a complex fraction form by replacing x to the negative 2 with 1 over x squared in both the numerator and denominator. To eliminate the complex fraction, simply multiply by x squared divided by x squared, which is a form of 1. This will lead to the final rational function expression of 1 divided by x squared minus 1. We now need to think about the interval of convergence for this power series. We have converted the power series into a rational function. We need to now think about where it converges. Remember that this is based on the convergent geometric series formula, which only converges when r is between negative 1 and 1. What replaced r in our formula was x to the negative 2. That means we need to place x to the negative 2 between negative 1 and 1. You'll see down here that I have done exactly that. The difficulty on this problem is recognizing that I need to take the reciprocal. When I take the reciprocal, it still gives me that x squared is between negative 1 and 1. The difficulty lies in understanding that even though you need to take the square root, it's still going to need to be between negative 1 and 1 because it originally was between negative 1 and 1. This means that our function will only work provided that x is between negative 1 and 1. Again, this does not tell you anything about convergence at the endpoints, negative 1 and 1. To check convergence at the endpoints, you need to replace the x in the formula with both negative 1 and 1. In this case, if you replace them, note that you would be getting 1 over negative 1 or positive 1 squared raised to the nth power. Because either a positive 1 and a negative 1 squared are both 1, this leads to 1 to the n in both cases. Since we're looking at the sum, if you take the sum of 1 forever, note that this must diverge for the simple reason that the limit of the sequence as n goes to infinity of 1 to the n will not give you 0. And because of that, we know that it must diverge by the divergence test. Now let's take a look at another example. In the next example, example 3, we are given a power series, 1 divided by 3 to the n times x to the n inside the sum from n equals 0 to infinity. We need to find the function in its rational expression form and then find the interval of convergence. In this particular problem, you'll see that we were given the formula for the summand in 2 factor pieces, 1 divided by 3 to the n and x to the n. They're both to the n power, and to put it into the power series form using the convergent geometric series formula, we need to have one thing raised to the nth power. Thus, I pull the x to the n and the 1 over 3 to the n together to make one combined base of x divided by 3, all to the nth power. Once I have it in this form, I can use the convergent geometric series formula, a first over 1 minus r, or 1 over 1 minus x, to rewrite this with 1 over 1 minus, and our base is not x, but x over 3. Now, this is not a regular fraction because it has a fraction inside of a fraction, which makes it complex. To put it into a better form, simply multiply by the unit fraction 3 divided by 3. That will give you 3 divided by the quantity 3 minus x. This will be the rational expression for that power series. Now, where will it converge? It converges based on the value of the thing being raised to the nth power, in our case, x over 3. The magnitude of that must be less than 1, which means it must be between -1 and 1, just like a convergent geometric series. Multiplying all 3 parts of the inequality by 3 lead to x being between -3 and 3. Then you would need to evaluate convergence at the endpoints. In this case, if you were to plug them in, you would have the sum from -3 over 3 to the n, which would give you the sum of -1 to the n, or using the right endpoint, the sum of 3 over 3 to the n, or the sum of 1 to the n. Again, both of these series must diverge because the limit of the sequence in both cases does not go to 0. This one will be 1 forever, and this one alternates between -1 and 1, meaning that the even terms and the odd terms go to different values. Thus, the limit does not exist. This means that the interval of convergence for this particular problem has to be from open -3 to open 3. Now let's look at example 4. Example 4 is quite a bit more complicated than the first 3. In this particular problem, we are given a power series representation and we want to convert it back to its rational function expression. Then we'll find the interval of convergence I. When examining this, your first instinct may be to get both of these with the same power. They do both have the power of 2n minus 1, but unfortunately the bases do not match. Since the bases do not match, you will not be able to write them into any combined form by factoring out a common factor. This means that you'll have to instead split up the power series representation into 2 different series. This will give you the series from 1 to infinity of 1 over x minus 3 to the 2n minus 1, minus the series from n equal 1 to infinity of 1 over x minus 2, also to the 2n minus 1 power. First, we're going to look just at the first series, and then we'll use the same technique to develop another representation for the second series. To take the first series, we need to again get it into that typical power series format based on the geometric series formula. Here again is our representation for the power series with its rational function expression based on the formula for a convergent geometric series. To take the first series, 1 over x minus 3 raised to the 2n minus 1 power, I first need to get a base being raised to an n power or a 2n power. The difficulty is I have a 2n minus 1 power, which will not be allowed. To get rid of the 2n minus 1 power, I need to multiply by another x minus 3 to lift the power from 2n minus 1 to 2n. I multiply by a unit fraction in the form of x minus 3 divided by itself. That will put x minus 3 in the numerator and change the power in the denominator to 2 times n. This will enable me to then pull the x minus 3 in the numerator away from the rest of it so that I can think of it as 1 over x minus 3 quantity squared to the n, or x minus 3 to the -2 power to the n. You could also pull the 1 in the numerator into the base and write it as 1 over x minus 3 quantity squared, all to the nth power. Any of those three forms would work. Now I'm going to apply the similar type of expression to the second series that I had above by applying the same algebraic tricks to get it written in a different formula so that I have some variable here inside of a binomial multiplied by the base raised to the nth power. You may want to pause the video here, work out the second one yourself, then turn the video back on to see if your answer matches mine. Moving on, the next thing that we see is that we are able to then write the second one in a similar format. Now that I have them both in this format, I can again use that formula for the convergent geometric series to rewrite this in terms of a rational expression. Note that the binomial factors x minus 3 from the first term and x minus 2 from the second series are not a part of this expression of the rational. They will be in addition to it, so you will get 1 times the x minus 3, or written here, 1 over 1 minus the base, 1 over 1 minus the base, then multiplied by those binomial factors. This will move the binomial factors to the numerator. Unfortunately, this does mean we again have complex fractions, since we have a fraction inside the denominator. That means we need to multiply by a unit fraction to eliminate the complex part of the fraction. This leads us finally to the following rational expression for the original power series. The next thing we want to look at in this video is multiplying power series together. When we multiply power series to create new power series, it is a far more difficult process, as you might imagine. Because you can think of a power series as basically an infinite polynomial, multiplying two power series is like using the distributive property, taking an infinite number of terms and distributing them over another infinite number of terms infinitely often. It can become very difficult to figure out what the formulas are. Fortunately for us, a French mathematician named Augustin Cauchy did this for us. For two basic power series centered at 0, one converging at a function f and the other converging at a function g over some common interval I, as given here in the blue box on the screen, can be multiplied together to get another convergent power series that will converge on the same interval of convergence as they have in common, and will converge to the product of what they individually converge to. In other words, if c sub n x to the n converges to function f, and d sub n x to the n converges to function g, then multiplying the two power series together will give me a power series that converges to f times g on the same interval of convergence they have in common. We call this the Cauchy product of the two series in honor of Augustin Cauchy. The proof of this is far, far beyond the scope of this course, and we will not even attempt it here. This is, in fact, a more difficult process, and we will not focus very much on multiplying power series together. However, I do want to expose you to it and give you an example of what it looks like. Let's see how the formula is used. You'll see that when you multiply the two power series together, you get a third power series where the coefficients are given by this E sub n. E sub n is written as the sum of a bunch of different terms, which consist of products of the coefficients of the two original terms, but not in the order you might expect. Let's use the subscripts k equals 0 and k equal 1 and the formula given here to understand where this series of numbers came from. In this formula here, It turns out that the coefficients of the series are themselves generated by a series. In other words, E sub n is itself a series, meaning that you have a series inside of a series, or nested series. This means that in order to know what the coefficient of the nth term of the product is, I need to compute the following series. However, notice that this series on the inside of this infinite series, the coefficient one is not infinite, it's finite. It stops at n. That means that we're going to take c sub k and multiply it by d sub n minus k. Let's let k be 0 now. To find e sub 0, the very first coefficient in the product representation for the product of the two power series, I'll take c sub 0 and multiply it by d sub n minus 0. N minus 0 would give me n, so e sub 0 would be c sub 0 times d sub n. What about the next one? If I let k be 1, then I would use c sub 1, and I would multiply it by d sub n minus 1. This gives me the next one. If I wanted, I could do a third one as well. And in the third one, I could write something like the following. For k equal 2, I would use c sub 2 times d sub n minus 2. This gives us the third term in the sum, which will generate the nth coefficient of each term in the product series. Now let's do an example and show us how to apply this formula. Before we do that, we'll cover just a few more ideas. Again, basically, what we're doing is we're taking two power series and multiplying them together. The two series must converge on a common interval I. One will converge to F, the other to G. Their product multiplied together will converge to F times G on I, and their constants on this product will be given by another finite series consisting of this expression. In example 5, we're to find the power series of F times G when we're told that F and G are both the sum from 1 to infinity of x over 2 to the nth. The first thing we need to do to apply this is to take a look back at our theorem up here. Notice in our theorem that both of the original power series are written in a format where the x sub n is separate from the coefficients. We need to take our series given here, x over 2 to the n, and separate it so that we can have x to the n by itself. This will pull the 1/2 to the n off on both of them. Our f and g are identical, which means that both c sub k and d sub k are 1/2 to the nth power. Those are the coefficients to each of the original power series. In the formula up above, the coefficient for the product is given by the finite series from 0 to n of c sub k d to the n minus k. That means that we're going to take this formula here and use that to find the coefficients of the product. I can replace c sub k with 1/2 to the k and d sub n minus k with 1/2 to the n minus k. Because these were identical, the bases are the same, both 1/2. That lets me add their powers of k plus n minus k, which just gives me the nth power. This gives me the sum from k equal 1 to n times 1/2 to the n. What is difficult to recognize here is that while n is the index of summation for the product, it is not the index of summation for the coefficients. The index of summation for the coefficients is k. That means that in this representation, 1/2 to the n is considered a constant and can be pulled out of the series since it does not depend on the index k. This will let me rewrite it as 1/2 to the n times the series from k equal 1 to the n times 1. You may remember way back at the beginning of chapter 5 that there's a formula for the sum from k equal 1 to n times a constant, and that's simply n times the constant. Our constant in this case, of course, is just the number 1. This gives me n times 1 to represent this entire series. That means that I can write my E sub n, my coefficient of the product series, as n times 1 over n to the nth. This means that f times g has to be written as the coefficient n times 1/2 to the n times x to the nth. Now I could combine the two ringed in red into one combined form since they both have the nth power and write it as x over 2 to the nth. This is purely a matter of preference and I do not have one. Let's move on to the next part. In the final part of this video, we want to do examples that show how to differentiate and integrate power series to generate other power series and to represent different functions in their power series format. We've already looked at several of these in section 6.1 in the video Power Series and Functions. Because of that, I will only work 3 different examples in this part of the video. Briefly to remind you, if we are given a power series and a function where the function has the format of some constants times x to the n in its power series form, we can expand it to write c sub 0 plus c1x plus c2x squared and so on. Remember the c sub n are the coefficients corresponding to each term of the series. C sub 0 is the coefficient of the 0th term, or the first one. C sub 1 is the coefficient of the k equal 1 or n equal 1 term, in this case, the second in the series. If we know that this power series converges on some interval I, then we can take the derivative term by term to generate this series of numbers and expressions. This is done by taking the derivative of each individual term. Since c sub 0 is a constant, its derivative is 0 and it doesn't show up in this list. If we take the derivative of c1x, the x, of course, its derivative is 1, so we get c1. If we take the derivative of c2x squared, the 2 comes to the front, gives us 2 times c sub 2 times x. We can also integrate term by term. If we integrate term by term, the integral of c sub 0 would give us c sub 0x. The integral of c1x would give us c1x squared divided by 2, and so on. Notice that we would also get a constant added on at the end. In other words, in order to differentiate and integrate power series, we do it term by term. When we do this, we are guaranteed that it will converge on the interior of the same interval of convergence as the original power series f. However, when you take the derivative and the integral of a power series term by term, you must recheck the endpoints. It's possible that differentiation or integration of the power series will change the behavior of convergence at the endpoint when you compare it to the original series. Here is the theorem in the book that applies to term-by-term differentiation and integration for power series. You'll notice that in this format, they've based it not on a series centered at 0, but on a generic series centered at x equal a. If x is equal to a and a is not 0, then the interval of convergence will be from a minus r to a plus r, where r again is that radius of convergence, which accounts for half the width of the interval of convergence. If we're told that it does converge on some finite interval of convergence, then we know that we can differentiate it term by term, and it's guaranteed to converge on the interior of the interval. We will have to recheck the endpoints. We can do the same thing for the integration, but again, you must recheck the endpoints. We did several of these types of functions in the section 6.1 Power Series and Functions video, but we will work several more as well. There's one last theorem to consider before we attack the examples. Let's suppose that we have a function f and the power series for f centered at x equal a. Is it possible that we could have gotten a different power series for the function centered at the same value x equal a if we had just used a different technique? The answer to this question is actually no. It is, however, far beyond the scope of this course to prove it. So for now, you will simply have to accept that in fact, if you find a power series representation for a function, that it is in fact unique, and that it is the only one that is possible at that center. Now we're ready to look at some of the examples for differentiation and integration. In example 6, I am told to expand the power series and differentiate term by term to find a power series expansion for the derivative of the function f. The first thing I did was to rewrite x to the 2n as x squared to the nth power. When you have one base and two powers, you multiply the powers together. This puts it more into the power series formula. You'll see here that what I did was generate the first 6 terms. You may want to pause the video here, find the 6 terms on your own, then turn it back on to compare your answers and see if you get what I got. To continue, by plugging in n equal 1, then n equal 2, and so on, I can generate the first 6 terms in the series. Notice that the 6th term actually corresponds to n equal 5, since n equals 0 is the first one. This generates the numbers 1 plus x squared plus x to the 4th plus x to the 6th, and so on. Doing the derivative term by term means take the derivative of each term individually, just as you would have done in a Calculus 1 course. That generates the list of numbers 0 plus 2x plus 4x cubed plus 6x to the 5th, and so on. In the next line, you'll see that what I've done is try to come up with a power series representation for this that is more like what's in a geometric formula. And fortunately, my efforts to manipulate the subscripts to get it into a better form were not, they did not produce a good result. The issue, of course, here is that I took the power series representation for the function, which was given to us as x to the 2n, and I applied the derivative with respect to n to it directly, or rather with respect to x. This should be an x here. It looks a bit like an n, but it is in fact an x. Make that a little bit more clear. When I take the derivative, that pulls the power of 2n to the front using the power rule and reduces the power by 1. I was trying to manipulate the powers to rewrite the power so that it wasn't 2n minus 1, but simply 2n. I thought perhaps that by pushing this forward by 1 and backing this up by 1, I could get there. However, if you replace n with n plus 1, note that you can replace only the n, not add 1 to the power. This gave me 2n plus 2 minus 1, which is 2n plus 1. In other words, it didn't help. I still have something with an additional term in the power. So I thought of doing it a slightly different way, which was simply to do this. Since I want to get rid of the extra minus 1 that's in the power, I am short by 1 power of x. so I can multiply by a unit fraction equal to the number 1 in the form of what I need, x divided by x. This will give me one additional x power to add into the x to the 2n minus 1, which will enable me to write it as x to the 2n. This does give me an additional x power in the denominator, but that x power is not dependent on the index of summation, so it could be brought outside of the power series. Unfortunately, because of the 2n that appeared in the numerator, I will not be able to write this in a strictly geometric fashion. N does depend on the index of summation, so it cannot come out of the power series, nor can it be combined into the base being raised to the nth power. However, you can still find what this is the power series representation for by remembering where it came from. If we scroll back up, you can remember that this is the power series after differentiating this term by term. So I can figure out what that is the power series for by applying the derivative to my original function, 1 over 1 minus x squared. You'll see here that I've recopied the problem so that you know what the original function was, 1 over 1 minus x squared. Then I rewrote it in the numerator with a -1 power and applied the power rule. This led to 2x over 1 minus x squared quantity squared. In other words, this representation here, now in a purple box, this power series formula is the power series for this rational expression or rational function, also now in the purple box. Let's take a look at the next example, which is example 7. In example 7, we are to integrate the given series term by term so that we can obtain the corresponding power series expansion for the indefinite integral. When we do this, we're given the function 2x over 1 plus x squared. We're told that it's equal to this power series formula. On a test, I will not necessarily give you the power series formula. You should be able to be given 2x over 1 plus x squared and write it in its power series form. Let's see how to do that. First, recall that you have to make it look like 1 over 1 minus something in parentheses. To do that, I pull the 2x away from it from the numerator to the front. That makes the numerator a 1. I do have the 1 at the beginning in the denominator, so it's fine. The formula, however, is 1 minus r, or 1 minus x for the power series. That means I need to rewrite the plus as a double negative. The first negative is the subtraction, but the second negative becomes a part of the base being raised to the exponential n inside the power series. This means that negative x squared becomes the base of the power series. Don't forget when you're done to write the coefficient 2x as a coefficient of the power series as well. I can take the negative that's inside the base and pull it away from the x squared. This will let me write it as -1 to the n, giving me an alternating series, times x squared raised to the n, all inside the power series from n equals 0 to infinity and multiplied by the 2x that originated from the numerator. Now that I have this format and it's more simple, I can take the x on the outside and pull it inside to be combined with the x to the 2n power. That would raise the power by 1 to x to the 2n plus 1. I could move the 2 inside as well, but it makes sense to leave it on the outside since I want to integrate term by term. I know that if I have the integral of a constant times the integrand, it's the same as the constant times the resulting integral. I'm going to leave the 2 on the outside and integrate the function by integrating the power series representation for it. When I integrate the power series, remember that I am integrating with respect to x, not n. That makes anything that depends only on n, such as the -1 to the n, basically into a constant. When I do that, that is going to let me write this out in terms. And again, you'll see here that I wrote out, I believe, the first 6 or 7 terms again by taking them and letting n be 0, then 1, then 2, and so on. By taking the integral term by term, I was able to generate this list of numbers here. The 2 is still on the outside. Finally, I will distribute the 2, which will cut each of those denominators in half. Looking only at these values here, I'm able to rewrite that into a power series formula, which would look like the sum from 1 to infinity of -1 to the n plus 1, x to the 2n divided by n. How did I come up with the formula? First things first. To find the formula, you know you have a series. Go ahead and put the series mark. Leave off the lower index of summation. It may well be one of the last things you fill in. The first term is sometimes not helpful to find the pattern. Let's look at terms 2, 3, 4, 5, and 6. In this case, I can see that all my powers are even numbers. Since this is the first one and this is the second one, it looks like if I multiplied the power by 2, I could get the right, or multiplied the index by 2, I'd get the right power. That gave me x to the 2n. Division, however, they're not doubled. They are simply the index itself, the first, the second, the third, the fourth. That gives me x to the 2n divided by n. The next thing to note is that it is alternating in sign, so I have -1 to some power. The power could be n plus 1 or n minus 1, or it could be n. I think I should start at n equal 1 so that I can get x squared over 1 for the first term. Since it's positive, I need the -1 to be positive. You could write this as either n plus 1 or n minus 1, and it would still generate the same list of numbers. Now let's take a look back at what the original function was, 2x over 1 plus x squared. In order to integrate that directly, I would have used u substitution, where u was 1 plus x squared. Du then would have been 2x. This would have given me 1 over u du, which is the natural log of the absolute value of u, or the natural log of 1 plus x squared, plus some unknown constant. This means that the power series you see here in green represents this function that you see here in blue, the natural log of 1 plus x squared. Now let's take a look at our final example for this video. In example 8, we are again told to use the formula for a convergent geometric series 1 over 1 minus r, written in the form of 1 over 1 minus x, in the power series formula, sum from n equals 0 to infinity of x to the nth power. We want to use either term-by-term differentiation or integration to find the power series for each function centered at the given point. In this case, our center is going to be at x equals 0, and our function is the natural log of 1 plus x squared. Based on our work in the previous problem, we know that when we had this, we integrated this function to get to here. If we're starting then with this, it may mean that we take the derivative to get back to here. Let's see how we can apply that idea on the 8th example. I'm going to define a new function that I'm going to call g to be the derivative of the function f. If I do that, then the derivative of natural log is 1 over u, or 1 over 1 plus x squared, times the derivative of the inside, which is 2x. This leads to 2x over 1 plus x squared. I can take this rational expression and rewrite it in the formula 1 over 1 minus x by pulling the 2x to the front to make the numerator a 1, and then rewriting the plus in the denominator as a double negative. The first negative becomes subtraction. The second negative becomes a part of the base being raised to the nth power in the power series formula. The 2x being multiplied by it simply tags along and multiplies by the power series representation. This will give me the power series representation for g, which is the derivative of f. However, I want the power series representation of f. So what is the relationship then between f and g? To get from f to g, I need to integrate the derivative, which means that f is the integral of g. In order to do that, I'm going to rewrite the expression I have for g by pulling the x to the inside and increasing the power on the x. That means I have to separate the negative from the x to the 2n power. That will let me separate the negative and pull the x from the outside to the inside and rewrite the base as x to the 2n. Since they're both base x, I can add the powers to get 2n plus 1. Now that I have this in a more simplified form, this is, of course, g. To get f, I need to integrate the derivative and integrate g. To integrate g, I will integrate the power series formula. When you integrate the power series formula, you are integrating from 0, which is our center, up to x using a dummy variable of t in place of the x in the power series. This is an application of the fundamental theorem of calculus, the part we rarely ever use. When we do this, remember that this is simply going to give me the value of this thing evaluated at the upper limit. Integrating this term by term will lead to the integration of the formula, which gives me x to the 2n plus 1 adding 1 and dividing by that new power, which is 2n plus 2. This will lead to the next line. You'll see here that I've rewritten 2n plus 2 as 2 times the quantity n plus 1. That gives me a common factor of 2 in the denominator to cancel with the 2 on the outside. It also, you'll see here in the numerator, I split the x to the 2n plus 2 into x squared times x to the 2n. The x squared does not depend on the index of summation, which is n. That means I could pull the x squared out of the power series sum, but I could also leave it on the inside. This will give me a power series representation for the function f, which is the natural log of 1 plus x squared. It can be written as negative 1 to the n x squared times x to the 2n, all divided by n plus 1. It is not possible to get this in a purely geometric form because of the n plus 1. That does depend on the index of summation. However, it does still represent the power series formula for the natural log of 1 plus x squared close to 0. This is the end of this video based on section 6.2 from the OpenStax Calculus book, Volume 2.